In this video, we're going to focus on solving first-order ordinary differential equations. Alright, so let's start. Now, if dy dx is f of x, then the solution would be y equals the integral f of x dx plus c. Okay, as an example now, let's solve dy dx is equal to x squared, where the initial condition, the boundary condition in this particular case, is y of 0 is equal to 5. So the general solution will be y equals the integral x squared dx plus c. Okay, we'll anti-differentiate x squared will give us x cubed on 3 plus the constant of integration. So the general solution gives a set containing an infinite number of curves, because c could be any value here, we don't yet know. Until we look for a particular solution, and we're told that at x equals 0, y is equal to 5, and so we substitute x equals 0 into our general solution. So we have 0 cubed on 3 plus c equals 5. So that means c is equal to 5. And the particular solution then becomes y of x equals x cubed on 3 plus 5, where y of 0 equals 5 is called a boundary condition. Let's solve another example. Let's say we're given x squared plus 4 times y dash of x is equal to 2x plus 1. Well, let's divide both sides by x squared plus 4, and transposing gives us the first derivative, y dash of x by itself on the left, leaving us on the right with the rational polynomial 2x plus 1 on x squared plus 4. Now, so y of x will be then the antiderivative of that plus our constant of integration, which we shouldn't forget, and I should really include in all the steps. I've just left it to the end, but you should really include it in all the steps. Now, to find an antiderivative of the rational polynomial 2x plus 1 on x squared plus 4, we could write those 2x on x squared plus 4 plus 1 on x squared plus 4. Okay, common denominator, so it's still the same thing. Okay, it's just that this and this are now amenable to antiderivatives. Just notice the derivative of x squared is 2x, and so the natural log of x squared plus 4, if we now differentiate that, that gives us 2x on the original x squared plus 4. Okay, so antiderivative of 2x on x squared plus 4 is the natural log x squared plus 4. Over here, if you imagine there were a 2 here, and then a factor of a half out front, we would still have the 1 over x squared plus 2 squared, and the antiderivative of that would be inverse tan x on 2, but we've got that factor of a half there because there's only 1 here, not 2. The antiderivative of 2 on x squared plus 2 squared would be inverse tan x on 2, but there's only a 1 here, so we put a factor of a half out front. So that's a half inverse tan x on 2 plus our constant of integration. Let's just have another look at another example here, this one involving electric current. If the electric current I is given by the rate of change of charge Q with respect to time t, then solve I equals t times the square root of t squared minus 1, where at the time t equals square root 10, the charge is equal to 8 units. Okay, 8 coulombs. So t is equal to greater than 0, must be, it's time. Okay, I is equal to dq dt is equal to t times the square root of t squared minus 1, so that implies that q is equal to the antiderivative of t times the square root of t squared minus 1 dt, plus of course our constant of integration. Okay, now we're going to make a substitution with this one because this looks amenable to a substitution, because if you have a look here, if we let u equals t squared minus 1, then du is 2t dt. Okay, and we notice that we've got a t and a dt here, we're just missing a factor of 2, but if we put 2 here and we put a factor of a half out front, that takes care of that. So q equals the integral t times square root of t squared minus 1 dt is equal to a half times the square root of t squared minus 1 times 2t dt. Okay, the 2's cancel here, so we haven't changed anything. And that's equal to a half times the integral of the square root of u, substituting in du, and that's a half times the integral of u to the half du. Okay, that's easy to anti-differentiate, because that half, when we anti-differentiate, is raised by 1 to become 3 on 2, divided by 3 on 2, so that means we end up taking the reciprocal of that 3 on 2 to be 2 on 3 out front. The 2's cancel and we're left with 1 on 3, u to the power of 3 on 2, plus our constant of integration, okay, which is a third times in parentheses t squared minus 1 to the power of 3 on 2 plus c. Still don't know what c is yet. We're about to find that next. So that's the general solution. And now to find the particular solution. So we have q at the time t equals square root of 10 is equal to 1/3 in parentheses square root of 10 squared minus 1 to the power of 3 on 2 plus c is equal to 8. Well, square root 10 squared is 10, minus 1 is 9, 9 to the power of 3 on 2. Well, that's really 9 to the power of a half cubed. Well, 9 to the power of a half is the square root of 9, which is 3 to the power of 3, which gives us our 27. So we now have 27 on 3 plus c is equal to 8. Well, 27 on 3 is 9. 9 plus c, okay, that gives us 9 plus c, and that's equal to 8. And so c must be minus 1. So the particular solution for our given problem is q as a function of t is 1 on 3, parentheses t squared minus 1 to the power of 3 on 2 minus 1. And this is the total charge at any time t. All right, now, just one more thing. When we talk about dy dx equals some f of x, okay, just splitting the differentials and doing this, integral f of x dx. Okay, look, as a technique, that's okay, but strictly speaking, it's not correct because y is a function of x and y changes with respect to x. And when we want to find the total value of y, okay, it's really the integral of dy dx. We really need to sum over all the x's, okay, to find the total change in y, to give us y. Okay, that gives us total change. Just neglecting the plus c here, but we really need to just, as a technique for solving differential, it's acceptable, okay? But strictly speaking, it's not correct because we're not summing the changes in dy. Y is a function of x, and y and dy dx is a change in y with respect to x. We need to sum over all the x's to get the total change in y. So instead of writing this, we should really write this. Okay, let's go down and have a look at another type of problem. I'm just going to flip this about a little bit. What if we've got dy dx is f of y, not f of x? Dy dx equals f of y, okay? Previous problems we've been looking at dy dx is some function of x. Okay, well in this case what we can do is we can flip the derivative. Dx on dy is 1 on f of y. And then x is the integral 1 on f of y with respect to y, plus our constant of integration. So let's have a look in the example here. Okay, dy dx equals 1 on y. Okay, and we're given the boundary condition y of x equals 3 is equal to 4. Okay, so dy dx is 1 on y. That implies that dx dy is equal to y. Okay, now I have split the differentials here. That's just a technique if you like. Dx is y times dy. And so the integral dx is the integral of y dy plus c. That will give us x equals y squared on 2 plus c. And that implies now that if we subtract c from both sides, we have x minus c is equal to y squared on 2. And that implies that 2 times, in parentheses, x minus c is equal to y squared. Okay, I'm going to get y by itself because we have given the problem y of x equals 3 is equal to 4. Okay, so let's do it that way. Okay, so y equals plus or minus square root of 2 times x minus c in parentheses. Okay, now particular solution, y of 3 is equal to plus 4. Okay, well what we can do is we can square both sides to get rid of the square root sign, and we'll get a 16 on the right. So we're left with 2 times in parentheses 3 minus c is equal to 16. Okay, dividing through both sides by 2, we get 3 minus c is equal to 8. Okay, now 3 minus something is equal to 8, so c is negative 5 because 3 minus 5 will give us 8, so c equals minus 5. Let's substitute that in, so we have therefore y equals positive square root 2 times x plus 5 in parentheses there. Since y is positive value 4 at x equals 3, we'll choose y of x is equal to plus the square root of 2 times x plus 5 in parentheses. Okay. Now, here's another one. Let's have a look at this one. This one is going to yield some interesting result with a constant at the end. Let's solve dy dx is 2y. Okay, well, flipping that again, dx dy is 1 on 2y. dx is 1 on 2y dy. Okay. Again, I have split the differentials just to perhaps indicate why flipping it upside down is such a good idea. Dx dy, and then multiply through by dy, puts all the y's on one side and the dx's on the other. That's why we split this differential business, okay? But really, y is a function of x and y changes with respect to x, okay? So accept it as a technique. Okay, so that implies that the integral dx is the integral 1 on 2y dy plus c. Okay, so x is a half natural log of y plus c. Okay, let's subtract c from both sides. X minus c is a half natural log y. Multiply both sides by 2, so we have 2 parentheses x minus c is equal to natural log of y. Okay, now if we exponentiate both sides, then we get e to the power of 2 parentheses x minus c on the left. Now, e exponent to the power of natural log, okay, which is log to the base e. These two cancel each other out and we're left with just y. Okay, on the log laws, this gives us y equals e to the power of 2x in brackets, in parentheses, sorry, 2x minus c. Okay, now by the index laws, we can split those two things. They have the same base, e to the power of 2x times e to the power of minus 2c. Okay, that's perfectly okay with the index laws. Okay, just simply add those together to give us back the original. Now, notice this second bit here. This, even though it's exponentiated, c is a constant, and so this whole thing's just a constant. We don't need to make it look so complex looking. We can simply call that the constant a. Okay, a is equal to e to the minus 2c. And then the general solution just simplifies so that y of x becomes this constant a times e to the power of 2x. Now, if you look at this problem, you can see that if dy dx was equal to some number times y, then that number, whatever it is, will be up here where the 2 is. So if that was dy dx is ny, okay, so if we had dy dx is ny for some number, n belong to the reals, some number, then our solution will be, okay, y equals a e to the nx. Okay, and we've taken care of the constant of integration. It's wrapped up in the letter a. All right, so, and perfectly acceptable. Okay, that's it. Finished with that one.